Good morning, friends. Now we are discussing numerical on the wind turbine. So the statement of the problem going like this. So the wind is blowing at a 10 meter per second and it is at 1 standard atmospheric pressure. The temperature of the blowing wind. So it is asked to calculate what is the total power density in the wind stream, maximum obtainable power density, the reasonable power density obtainable, the total electricity generated, what is the torque and the axial thrust. So it is given that the turbine is operating at 40 rotations per minute with the maximum efficiency, and the turbine diameter is 120 meter. So it is given that efficiency of the turbine is 40%. This 40% will be completely utilized. So before going to the solution, so the points to be remembered and the formulas to be memorized is like this. So the total power of the wind blowing is equal to the kinetic energy of the blowing wind. So the kinetic energy possessed by the blowing wind is equal to the power input. So that is the wind power we are taking. So that will be taken as the product of mass into kinetic energy. So that is the mass flow rate, that will be in kg per second. So that will be calculated using continuity equation. M is equal to rho into A into V. So and the kinetic energy is given as V square by 2gc. So this gc is 1 kg per Newton second square. So substituting this mass rho into AV and kinetic energy as V square by 2gc in wind power equation. So we are getting the total wind power as 1 by 2gc of rho AV cube. If you take Gc as 1 kg per Newton second square, so my total wind power is 1 by 2 of rho AV cube. Then maximum power, so that is given as 8 by 27 of Gc into rho into AV cube. Then efficiency or the power coefficient of the wind turbine is given as the output generated. So that is the electricity generated divided by the input power. So P max, so that is my output power. So that is electricity generated divided by this P total. So that is the input power. So that is the wind power. So we have two GC and GC gets cancelled here. So we get the ratio as 16 by 27. So that we put in decimals means 0.5926. So that means the wind turbine is capable of converting less than 60% of the total wind power to the useful power. That is, out of the total wind power available, only 60% of the wind power will be converted to the useful power. Then torque produced is 2 by 27 of Gc into rho dV cube divided by N, and the axial thrust, that is the thrust offered by the blowing wind in horizontal direction, is pi by 8 Gc of rho into d square V square. So these are the formulas we are using in solving the numerical. So now taking the given data here, so the blowing wind is at the velocity of 10 meter per second. So then it is at one standard atmospheric pressure. So one atmospheric pressure is equal to 1.01325 into 10 to the power of 5 pascals. Pascals is in Newton per meter square. For air, the gas constant capital R is given as 287 joules per kg Kelvin. So from gas equation, I can write my air density rho as P by RT. So P is the atmospheric pressure. So that is given 1.01 into 10 to the power of 5 divided by R. So that is 287 joules per kg Kelvin, and temperature it is given that 15 degrees centigrade converting into Kelvin. So by adding 273 to 15 degrees centigrade, it is 273 plus 15. So we are getting air density rho as 1.226 kg per meter cube. Now power density, so that should be in watts per meter square. My wind power, so that is taken as here the wind power as 1 by 2 into rho into AV cube. GC value is 1 kg per Newton second square. So it is half of rho AV cube. So that is my wind power. So that half of rho AV cube divided by A. So A and A gets cancels both in numerator and denominator, because my power density will be in watts per meter square. So watts, so that is the wind power in the numerator, and area, turbine area. So considering the diameter of the turbine, we are calculating the turbine area. So but the a in the numerator gets cancels with a in the denominator, so the equation is now half of rho v cube. So my rho is now air density 1.226, and v is the velocity, so that is given here as 10 meter per second, so that we are substituting v as 10 here, so it is 10 cube. So we are getting 613 watts per meter square. Now power density, so that is the output power what we are getting. So that is also in the watts per meter square. So we have a power maximum power obtained. So that is 8 by 27 of rho AV cube. So we have A in the numerator. So in the denominator we have A here. So both the A's gets cancels. We have 8 by 27 of rho V cube. Substituting the air density and velocity here. So we are getting output power. So that is 363 watts per meter square. So if we are having 100% efficiency, so then the wind power density is 613, but the wind turbine is capable of utilizing 40% of the total wind power. So considering efficiency as 40%, so it is now 0.4 times of this P total divided by A. So that is 613. So 0.4 into 613, we are getting 245 watts per meter square. Then total power to be obtained using this power density, so that is P by A, so that is equal to 245. So taking A to the other side, we have total power P is equal to 245 into A. So A is nothing but the turbine area, considering the diameter 120 given. So now the power is in watts. So divided by 1000, so we are getting power in kilowatts. So the total power generated is now 2.77 kilowatts. Now torque and axial thrust will be calculated using the formulas. So here N, that is rotations per minute of the turbine. So that is given as 40 RPM. So it should be in rotations per second, so that's why it is divided by 60. So we are getting in newtons. So axial thrust, so the answer what we are getting is in newtons, so divide by 1000, so the final answer will be in kilo newton. Thank you.